Hello everyone, this is KINGSINE. Today we'll guide you through our protection relay testing workflow using KRT software. Step by step, you'll see how to create tests directly from a relay setting sheet and save the setup as a user template. With this template, you can easily load everything on site, saving valuable time by preparing it in advance from the office or at home. Now, let's open the KRT software. The first step is usually to select the appropriate test template for the relay. These templates are already organized in the software, so all we need to do is choose the one that matches our specific relay model. Once selected, we'll see that the relevant relay information is automatically populated in the KRT system. Next, we import our configuration file in .rio or .xrio format. This way, we don't have to manually enter each relay setting one by one. Instead, with the combination of the test template and the configuration file, all relay settings are automatically assigned in the KRT system. Today, we'll take a slightly different approach. Instead of relying on pre-configured test lists, we'll build the entire test sequence step by step. This hands-on method will give you a clearer view of how KRT works at its core and showcase its flexibility in test creation. The relay calculation sheet we're using is the same type of document typically provided during field testing projects. It contains all the key parameters we need: protection settings, curve characteristics, device specifications, and more. First, let's click on a test module to enter the test center. As we can see, the test object is automatically created. Now, we'll configure this object to match our specific relay. The first step is renaming the test object to reflect the actual relay we're working with. To do this, select the default name, click Rename, and update it with the relay's identification. In this example, we name the relay according to its incoming and outgoing lines, TB, SW110 and TE, SW110P5F30. Proper naming is essential for keeping documentation clear and well organized. Next, let's move on to the device information settings. Here, we'll manually enter additional details about the relay, such as the manufacturer, device type, serial or model number, and substation name. These key details are important for accurately identifying the device and keeping records complete. Now, we need to set the nominal voltage and current values for both the primary and secondary sides. For example, our primary line-to-line voltage is 13.8 kV, while the secondary is 110 volts. The KRT software automatically calculates the ratio between these values, ensuring accuracy during testing. Next, we'll align these settings with the relay under test. All of this configuration data, including the test object details, will be automatically recorded and included in the final report for reference. Next, we'll add specific tests based on the relay setting sheet. For this first device, we need to test three types of overcurrent functions: definite time overcurrent, inverse time overcurrent, and ground fault inverse overcurrent. To begin, we'll open the overcurrent section. Here, we'll find 5 element types available: phase to phase, phase to ground, positive sequence, negative sequence, and zero sequence. And here's the challenge: we need to run 3 different overcurrent tests, each with its own unique function. So how do we manage that? It's actually quite simple. Within the overcurrent page, we can add multiple function modules to a single test object. For each test, we just enable the corresponding function module. This allows us to test all 3 overcurrent conditions efficiently, without reconfiguring everything each time. Now, let's add the tests from the sheet one by one. First, we'll set up the instantaneous overcurrent protection function. We add one element, name it 50, then select the definite time curve from the curve library. Next, we set both the pickup current and pickup time according to the sheet values. Once done, we click Apply to save the settings. Next, we'll move on to the inverse time overcurrent test. Here, we right-click within this section and select Add to create a new function module. We add one element, name it 51, and select the extremely inverse time curve from the curve library. Again, we configure the pickup current and inverse time as specified in the sheet. Once these settings are confirmed, we'll click Apply to save them. Finally, we'll add the last function module for this device. Right-click in the section again and select Add to create the new module. This one will simulate ground fault protection. We'll name the element 51N, choose the definite time curve from the library, and enter the pickup current and time values exactly as specified in the sheet. When finished, we'll click Apply and Exit, saving all settings and returning to the main Add Test interface. In the left Test Center panel, right-click the test object we created and select Add Overcurrent Test. To keep things organized, right-click again to modify this test. For the first test case, we'll name it 50 in the Test Center display and select the corresponding function module we set up earlier to activate it. Once the function module is applied, the protection curve loads automatically. Next, we add test points. Click Add Multiple to define the current range by setting the start value, end value, and step size. Then, select the fault type and angle. The system automatically generates the qualifying test points based on these parameters. Finally, click Add to Table, and all valid test points are populated in the test list. As you can see, all qualifying test points have been successfully added, completing the setup for the instantaneous overcurrent protection function. For the inverse time overcurrent protection, we follow the same steps. Right-click to add an overcurrent test, modify the name and function module, and then configure and add the test points. The same process applies to ground fault protection. We'll add test points based on the predetermined pickup current to ensure complete test coverage. With all overcurrent protection tests configured, we can now move on to undervoltage and overvoltage protection. For these tests, we'll use state sequence test modules, creating different system states to accurately simulate dynamic transitions in the power system during testing. Next, we'll right-click the test object to add a state sequence test module. Right-click again to modify the name, clearly distinguishing between overvoltage and undervoltage test cases. Here, we name the undervoltage test 27. Then we set up two states, one for normal state monitoring and one for undervoltage condition monitoring. Starting with the normal state, click Nominal and Balance to quickly set all three voltage phases to their standard values. We then program a 1 second duration, so the system remains in the normal state for exactly 1 second before automatically transitioning to the fault condition. For the next state, we set the parameters to simulate the undervoltage condition according to the values in the setting sheet. Here, the primary line-to-line voltage is listed as 11.04 kV. From this, we calculate the corresponding secondary line-to-neutral voltage, which is 6.374 kV, and assign it to each voltage channel. Once the voltages are set, go to the View section in the top toolbar. We can choose to display values in either primary or secondary units, based on the ratio configured earlier in the test object. After entering the values as primary, switch the display mode to secondary. The system will automatically convert and display all values accordingly. Finally, for triggering, select binary mode, meaning the test stops only when the tester receives a trigger signal from the relay. This setup ensures accurate simulation and smooth operation, making the testing process both efficient and reliable. With the undervoltage test complete, we now move on to the overvoltage test, which is very similar and also uses the state sequence function. Following the same steps, we add two states, the first for normal operation, and the second to simulate the fault condition. For the normal state, click Nominal and Balance to quickly set all three voltage phases to their standard values, and set the trigger to time as 1 second. For the next state, we set parameters to simulate the overvoltage condition based on the setting sheet. The primary line-to-line voltage is 16.56 kV, from which we calculate the corresponding secondary line-to-neutral voltage of 9.56 kV. This value is assigned to each voltage channel. In the View section, set the display unit to primary and enter 9.56 kV for each channel. Then switch the display unit back to secondary to view the calculated secondary voltages based on the configured ratio. All test items for the first protection device have now been added. Scrolling down, we can see that the test configurations for the subsequent devices are identical. To save time and ensure accuracy, we can copy the test items from the first test object and modify each new test object's name accordingly. To do this, right-click the original test object and select Copy to create an identical duplicate. Then, right-click the new copy, select Modify, and update its name to reflect the corresponding feeder circuit. This naming convention ensures clear device identification. By copying the settings from our first reference device, we can quickly apply the same test configuration to all other relays with identical test tasks, greatly streamlining the setup process. Now, we can skip relays on the sheet that share the same test task and settings. Now, let's take a look at this relay. This test covers overcurrent differential protection, using the differential test module in KRT. Since we are testing a transformer, we select transformer as the protected object type. As only 2 windings are involved, we set windings to 2 and choose the measurement reference winding. Under Balance Coefficient Calculation method, we select how the balance coefficient is determined, either by calculation or direct entry. Here, we choose Get the balance coefficient by rating, which calculates it based on the transformer's power, voltage, and CT ratings. Next, we configure the test object parameters according to the values in the settings sheet. The sheet includes settings for both overcurrent differential protection and percentage differential protection. We'll start with overcurrent differential. The power rating is 10,200 kVA, so we enter 10.2 MVA in KRT. Since this is a transformer, the primary and secondary power values are the same. For voltage, we enter the nominal values for each winding: primary, 34.5 kV, secondary, 13.8 kV. Under vector group, we define the winding connection type, Y for star and D for delta. On the right side, we select the calculation model for I-bias. I-bias is determined based on the protection model provided by the manufacturer. In the differential current settings, we enter the startup current from the sheet, 0.329 amps, and set the quick break current to 2.96 amps. For differential time settings, current and time tolerances are configured according to the relay's specifications or hardware parameters. If parameters are imported from a template, these values are pre-configured based on the specific protection model and usually do not require manual adjustments. When evaluating test results, the pass or fail criterion is determined by taking the maximum of the relative and absolute tolerances for both current and time deviations. Once all settings are configured, click on the characteristic graph to preview the curve. In the function module section, name this test 87T overcurrent and click Apply to save and activate the settings. Next, we add the test points, completing the overcurrent differential protection setup. For percentage differential protection, we copy the function module from the overcurrent differential test, rename it 87T%, and adjust the CT ratios, primary, 200 amps, secondary, 1 amps and 400 amps to 1 amps. We set the startup current from the sheet to 0.169 amps and the quick break current to 5.76 amps. To configure the characteristic curve, click Characteristic Graph, then select Tool to enter the inflection points and slopes according to the settings sheet. Click Apply and Exit. To add test points, simply click directly on the characteristic graph to place them. This completes the percentage differential protection setup. Next, we quickly configure the entire test sequence according to the requirements in the settings sheet. Once all required tests are added to the KRT test center, we can save the configuration as a user template. This allows the setup to be quickly loaded during on-site testing, saving significant time since the template can be prepared in advance from the office or at home.